A three, two, one. So this whole thing has been, about the past 2.5 years of thought experiments. Some of it's based on work from Michio Kaku, Stephen Hawking, Carlo Rovelli, and of course, all the classic physicists of the golden era. A lot of these ideas I'm looking to build on, test them, and further explore how they really apply to the universe. So, the first thing we have to start with is the self fulfilling prophecy uh, of existence, that if we can observe something, then something must exist. Because even in a type of simulation or projection, in order for that to exist, something must exist outside it or holding it together. So you can't have nothing in the universe as we know it. There must be something. This is why I subscribe to the idea that the zeroth power or the zeroth dimension reverts back to the first dimension. And I know that's pretty typical for mathematics to go along with that. But there's still people not on board. So dimensions are really what drove this. It was kind of an arbitrary starting point for me. But, as a if you're a physicist, you well know that Minkowski added this fourth dimension of time to the equations, and after dragging his feet a little bit, Einstein eventually adopted it and added relativity to account for certain things, and that made a very, very solid model for the universe. Now, a lot of research has gone into exploring higher dimensions, a grand amount that is very fascinating and interesting. But since some of the string theorists were going a little crazy and getting up to 9 or 11, or I'm not even sure what it's up to these days, I thought to myself, well, maybe we could work backwards a little bit, go for the lower dimensions. But then to even begin with this, we need to talk about what is time. Well, time can be defined simply as a series of events. Time, the way we traditionally describe it, is measured as a sequence of causality. And anytime we violate that, we have to adopt rules in physics so that it's possible. But simply a sequence of events is enough to describe time. And therefore, we can also use it to describe space. In other words, we're going to look at the universe if it was 4 dimensions of time, where distance and time are the same, where time is a series of events or states. So that means the first dimension is our string of events. So it's really important to describe what we're going to model this event as, to really help people get their heads around what I'm saying. Because, me personally, I like the visual aids and the moving physical objects in my mind. I know that's not something everyone likes, but this is where it came from, and that's how I'm going to describe it. So the first dimension exists. So let's say, right, we must assume at the beginning, if we had one dimension, it would exist. So this means it can be a potential infinite amount of events long, but we have to describe the depth, thickness, the other dimensions that we typically think of because of how we live in a 3D space / 4D space. So what is the width and what is the thickness? Because we know the length is a series of events. Well, it's somewhere between 1 and 0 because we know it can't be nothing and we know it can't be measured. Speaking of measurement, now is a good time to define our resolution. For this, we're going to use the well-proposed, calculated, and assembled idea of the Planck length / the Planck second, and these units being our smallest possible base units to measure. Now, we can't actually measure that small in the real world yet, but for calculations and theories, it's a great number because it's based off several other constants, which if you're a physicist, you'll know. If not, gravity's one of them. That's a pretty consistent one we can measure very well. So the thickness it can't be 0, and it can't be measurable. So let's say it could be approaching 0. Again, it would never reach 0, which would create a infinitely scaling form of the universe, which is, definitely something that's in certain models. But it wouldn't matter. What matters is it's less than 1, because we couldn't measure it in, say, the y or the z dimension. We can only measure it in one dimension at a time. That's why it's the first dimension. So we take this long string and we can do a couple things with it. Because there's no defining universe around it, we can loop it back in on itself. And that's still one dimension because we can't measure it in outside of that one dimension. We can fold it over itself, or we can stack many of these. And once they come in contact, you get something that violates what you had before, where there was only forward or backward potential paths for a series of events. Now, say you folded it in half, now an event doesn't have to go all the way along the length and then back across the top. It can simply go from the bottom to the top, as long as those are connected. It's almost like a one-dimensional wormhole. But basically, we folded space from the one dimension to make it two-dimensional. And we could keep folding or keep stacking layers till we get, our traditional, how do you describe the second dimension? It's a sheet of paper. We have X and Y. What's the thickness of the paper? Approaching 0, but not 0. Less than 1, but not 0. Which is a strange concept because, again, 0 is nothing and 1 is something. But for our purposes, it's not measurable. And we'll get into how this works later. So what do we do with this? Well, we take that sheet of paper and we fold it back over itself, or we stack them on top, and all of a sudden you have a stack of papers, or a cube. A cube is X, Y, and Z. You could make it a sphere if you prefer, because a lot of things in the universe, they prefer to be spherical. So since we have a three-dimensional object that we've constructed by explaining time events and what is really happening. So we get from the first dimension, which is a string of events, to the third dimensions, which means events can move, or an object, something that represents certain states, can move along these events in X, Y, Z, and can rotate, orientation, roll, pitch, and yaw. We sort of have a coordinate grid system in the third dimension. Now, the fourth dimension. This is the one that I would be most likely to probably step back on, but I think this is enlightening, at least to me. The next step being, how do you get to the fourth dimension? And the way we visualize that is the same way we did these other ones. We're going to stack layers. And what happens when you stack 3D shapes around each other? Well, first off, it looks a lot like, the very famous 4D representation in 3 dimensions, which is the tesseract. If you take a cube, inside a cube, connect the corners, that's our hypothetical diagram of a certain moment of the fourth dimension. Now, I've seen like animated versions of the Tesseract, and it kind of stretches and folds over itself over and over again. I propose that instead what is happening is the expansion of the universe that we observe is the fourth dimension of time. And as we follow time in one direction, overall, traditional time as we would describe it, these layers of the third dimension at a resolution of a Planck length, so it's a very small, imperceptible pixel, if you will, is expanding outwards. But it's just building layers and layers and layers. Where do those layers come from is a little more complicated. And are they just the third dimension expanding out? Or are there multiple universes, 3D universes, coming together? Those are both potential solutions that we've already been thinking of. So there's a good connection back there. Now, if you think about the first dimension, how would you make this first dimension longer? Well, you need new events to preserve energy, motion, momentum. And whatever law would make the first dimension expand would also make it expand on the second dimensional level as more events get added, and then the third, and so on. That's where we get expansion, is just the same driver at all dimensional levels. Now let's look back at this Planck length. Let's just take one Planck length of the first dimension. And because this is our measurable limit, our pixel, our 1 unit, we could break that one dimension down into a number line, essentially. But here's where something really cool comes in. Loop quantum gravity describes the universe a little differently than the string theory or other ways. The way I describe it is the chainmail universe, because it's like a interconnecting mesh. It's really cool. Carlo Rovelli had probably a more correct and better way of describing it than me and my chainmail. But essentially, there's little pockets that are both all at the same time, simultaneously, happening, the past, present, and the future. Now, what that means is we have distinct things, past, present, future, and it just so happens the smallest loop that you can make with unit lengths is a triangle, which has 3 sides. So past, present, future. So if we make a little triangle in the first dimension, what we'll notice about this triangle is along the x-axis, perhaps, you could measure it as one Planck length or one event. But in the y-axis, you can not measure it. Because it's a triangle, you don't reach one full unit in height. You're just short. Equilateral triangle. And that means you can fit past, present, and future into one-dimensional event. And here we're going to take it a step further, because we're talking about something we describe with 3 dimensions quite often. What is going to happen here is this is not going to be a triangle. This is going to be a tetrahedron. So actually you take your little D4 die, and this fits in one dimension because only one face can be measured at a time. Because if you're measuring that face, everything else is lower than your resolution that you can measure. Now, there may be potential other geometries that may have been described or may be described in the future, because I know there are other people working on geometric models of the universe, of the ether. Ooh, bad word, ether. This one works very well to explain the concept. So let's take these triangles. We're going to approximate a circle. So a circle has a ratio of 2 pi between the radius and the circumference. Well, 6 is kind of close to 6.2838 and so on. Now let's say you took these triangles, you took a point, and you tiled out. You get a hexagon. Well, what do you know? 6. Close to 6.28. But it's not the perfect resolution for a circle. So let's tile out hundreds and thousands of times. And eventually, you could get pretty close to an actual circle. But the outside would be jagged and wavy, but you'd get closer to that 6.2838 ratio. Now, scale outwards trillions of times, and even more incalculable greater numbers. You just keep adding zeros at the end forever. That kind of scale, you could not tell that it wasn't circular. But of course, it's wavy on the edge if you really were to zoom in. Now, that's an example in 2 dimensions. Remember, these are tetrahedrons, so really they don't tile out as a hex, they tile out as a 20-sided icosahedron. Now, there's something called the 500th cell, which is a fascinating geometric thing that has been greatly studied and has, within this pattern of tetrahedrons as they tile out, are so many other geometries that you could use to describe what is happening here. And that is just 500. And it's an insane, ridiculously complex mathematics. So imagine the scale of the universe, or even the scale of a single planet. So then, that's 3 dimensions. Well, when do you stop? Well, you keep expanding out with resolution. That's your 4th dimensional universal expansion. In other words, as our limit of ratio to 2 pi, as we get closer to that, as we approach a limit somewhere, the universe follows along with that. It follows the better resolution you get. But of course, you never reach the end. It's sort of the infinite coastline paradox. We have to draw a line somewhere, or else you could just say everything is infinite in both directions, and then you're lost. Now, because the universe is made up of time and events, this is going to change how we define our laws of the universe. So let's look at how gravity works in this context. A vinyl record has, commonly been used to show how when you're rotating 2 circles around each other, if you want them 2 points, one on each circle, to stay aligned, or the inside of the record to the outside of the record, the outside has to spin faster if you want to maintain that synchronous rotation. Now there's a torque between these 2 points. It's a rotational force that is going through the physical material of the vinyl. Now this doesn't describe gravity perfectly because these are the forces of a spinning disk, but what it does show us is the disparity, and we can find that disparity in our resolution. So if we take the smallest hex from before in 2 dimensions, it's easier to show. But this is really happening with the icosahedrons in the 3rd dimension. But the smallest hex we have, we can rotate around the point. So that can have 6 states, 6 different potential rotations that you could measure. Now, contrast that if we tile out further. That polygon has many more states of rotation, sort of. Because if each unit, each event is just changing states, you're just shifting each one unit and not, physically moving the whole shape. So 1 unit at a time, but now you have different speeds, don't you, if you go at 1 unit per second or something. So in 6 seconds, the first hex, the smallest hex, will have done 6 rotations in 6 seconds. But the outer hex might have done a third of a rotation. The polygon resists skipping a state. These 2 different orbits, we'll call them, are part of connected space, and they don't want to be out of sync. So suppose the small hex rotates 1 state per second, the larger hex rotates more states per second, but completes a rotation in 6 seconds. An object at this higher orbit would have to change its rate of velocity through time to keep up with the orbit. The other option, right, because the object wants to go at 6 states per second, but it has to go faster to keep that synchronization. So it must increase its velocity, or there's the other option here. It can lower its orbit. The object, which we're saying is a collection of states of time, of events, a cluster of time loops, can either speed up to stay synchronized with other collections of time loops, or it can fall towards them. Fall as in change to a lower orbit if it were orbiting. This is an approximate explanation of gravity. At this small of a scale, there's a lot of allowable error and not a lot of particles, which means the pull is not very strong. And typically particles so small, and no particle is actually this small. This is so much smaller than the scale of an actual particle that it's ridiculous. But particles that are small have, I'm talking subatomic particles with barely any measurable mass. They have a high velocity, which is so much higher than this force. That's why it takes a massive cloud of space dust for matter to even start to come together to make something heavier. But when you get a lot of these particles together in one area, there's more synchronization, more synchronicity, whichever term you prefer. And that brings in more particles drop to lower orbits. The force is amplified. Is also, again, it does force things to change velocities, change energy. So not only do you change individual particles' vibrations and thermally make them colder, the more things you have together, you also could slow down their velocity. Now, there's exceptions here, right? We all know what happens at the center of a very heavy, dense thing, and we'll get to that in a second. So just to reiterate, a particle is simply a collection of these Planck pyramids, these tetrahedrons, in a specific arrangement and shape. The pyramids themselves don't travel. They're just what space and time are, which space is 4 dimensions of time. Just think of them as pixels. But the collection of states, the information, the state changes. So a particle is just a code of orientations. And if that particle were to move 2 inches to the right, as it moves 2 inches, all of the Planck pyramids along that will shift and then shift back to something else as this particle passes through. This not only aligns with information theory, but there's a limit at how fast these orientations can update. And that limit is akin to c, or the speed of light in a vacuum. Now you may have noticed that there's other disparities here. So when you're far away from objects, you experience a different amount of events because you're less in sync with them. For any update of the space geometry to reach you, it would take so long you wouldn't even be in the same position anymore. At a certain distance away, the difference between you in one position versus another reaches the same potential synchronicity. So gravity doesn't move you any measurable amount. We can also just imagine it as gears. As if you have 2 gears, a little gear and a big gear, as you increase the diameter of the bigger gear, the ratio of rotations changes. So the smaller gear experiences more rotations the bigger the diameter of the other gear. And what's one rotation? Well, let's say that's one moment you experience. So whether you're traveling at a normal speed, you went around this whole circle, it would take you a very long time, the same amount of time as the little gear. But if you went the speed of light, it doesn't matter. The little gear still makes the same amount of rotations. The velocity doesn't matter to the number of rotations. So even though you experienced less time, the little gear made the same amount of rotations, and the people there weren't traveling at the speed of light, so they experienced a lot more time. I think that's a better description of it, and I think that should be taught somewhere, because that really cleared it up for me. When you're moving at the maximum frame rate of the universe, which is the speed of light, you don't perceive time, because you are that single state of events, and nothing around you would be perceptibly changing, because everything is constantly moving with you, changing state with you. You wouldn't be able to observe anything else changing state around you. And remember, these are events, these are time. So around you, you would not be able to observe any changes in event states beyond just you entering. So at the speed of light, you experience no traditional time. Now, small particles and light struggle to exist at the center of a gravity well, because the information organizes to synchronize. What this results in is in denser atoms. Now, everything's moving towards equilibrium, however, so eventually there's too much in one little space and trying to get even more synchronized. And so you eventually get hotter. Think of it as a Rubik's Cube. So the universe wants to reach equilibrium and solve the Rubik's Cube. But sometimes you have to undo one side that's done of the Rubik's Cube in order to solve multiple sides. This is where that energy buildup is. You have to get really hot in order to eventually release that energy to some equilibrium. To get everything synchronized, you have to bring it together and then spread it out. Light can convert to matter, but matter can also radiate light away. This is part of the universe's thermodynamic equilibrium that it is continuously working towards. Now, gravity, which we semi-described, is just one of the forces. All the forces are the same force. They're just applied at different scales. So subatomic particles, as we talked about before, and their building blocks, these shapes, they synchronize with each other. You need colored quarks together. You need bosons together. The proton, neutron, and electron, they all find alignments that form larger structures. You get strong and weak force. You get the atom. You get other configurations of the atom. You get Higgs fields, and so on and so on and so on. And we keep finding more and more things, except gravitons. We have not been able to find those. Now, energy is stored in their movements as well as their bonds. It is inherited from the synchronization efforts of the universe. The time sink effect between particles is what holds atoms together. Elements follow the same pattern as our gravity. The more particles you add, the denser and more stable they sometimes become. But of course, there's many configurations and shapes that don't quite fit, and that's where you get maybe a more reactive element in the middle of a sea of less reactive ones. The more particles you add, but eventually there's just too much. And again, we have that Rubik's Cube problem where we need to share some of the synchronicity, because everything can't all be in one place, and we get radioactive decay. Now, a lot of this occurs because of the high velocities of something like an electron, and it's such low mass that it's very easy for it to find a new position to be. So what that means is its mass is really its shape, within the geometry of the universe, and it has a much less complex shape than a proton. However, it fits very nice with a proton, and that's why they are attracted. It's almost like the receptors on a cell. Additionally, pertaining to electrons and subatomic particles is the electromagnetic field. This is still particles trying to synchronize. It scales with the amount of charged particles and as well as their proximity, because there are easier paths the closer you are to the center of it all. Now, this happens in all states of matter where charged particles can move. Now, electrons tend to move and the protons don't because they are less massive, aka less synchronized, different shape. It has more pathways to take, more options to fit, or more openings, more configurations of the puzzle where an electron fits, especially in a conductor such as iron. And that's why you get metals that share electrons, and occasionally certain other special substances and materials that can allow different conductions, because they are aligned in a certain way structurally on the atomic level and possibly subatomic level, that they can find multiple orientations of all the electrons in it equally synchronized. Now, once you apply an electric charge to something that is conductive, you change that equation. That's why electricity is all potentials, because it's where can electrons find the most synchronized home. So when you change that potential, and we can change it a lot, very high dangerous levels, a lot, or we can just change it a little, and you will get things to move. And I mean, we already know that those particles will bounce and move on their own just from surface contact. That's why we have static electricity. Now we look at states in other unique forces, which again are all one force, but they're different resolutions of it. So we have the tri-state nature of your quarks, of your weak bosons. Now you have the three classes of those. You have the quarks, which really only become particles when they have three colors. There are exceptions to that, but they don't really last on their own. You have to kind of force them to be. That hints at a smaller structure to it all. The tri-state, I think, is very important because, well, they must relate to each other in some relative version of the states of adjacent Planck pyramids. Now, the nature of thermodynamics and entropy are the arrow of forward direction of classical time, the one complete and total truth that we know about the current universe. You know, there's this eternal quest for equilibrium, and it's so strong, energy flows from high to low so much that even black holes will radiate and white dwarfs will eventually spread dust across the cosmos. Now, it'll take trillions of years, billions depending on the size of the black hole, but eventually, theoretically, all energy will be distributed equally across the universe. And that's why this is what I call all of this, the entire concept, entropic time equilibrium by universal geometry. Now, at first, black holes were kind of a troubling spot. I didn't know where they fit, but I did more research and figured it out. You have Hawking and his black hole entropy at the event horizon, which resemble the structures of Planck geometry. They use Planck triangles to describe the sphere, but because they're not quite triangles, they use a certain shape. So instead of 180 degrees, it has 360. So it's kind of a square because of the curved surface of the black hole. But what that really is that's the face of a tetrahedron that tiles with other tetrahedrons. They just used a different mathematics, more classical mathematics to describe it than I did. And maybe they're probably more correct. But the Planck pyramid does do a really good job of describing all this. So I'm going to stick with it for now. Inside that event horizon, there's still information. So this theory of energy and information cannot be destroyed. It's still there inside the black hole, but it is no longer in three-dimensional arrangements. The third dimension at that gravitational level gets so condensed, it no longer holds its structure, which means the information needs to be broken into unrecognizable fractions to be stored in unobservable lower dimensions. So when we talked about storing a single tetrahedron, which is three-dimensional information, but it can only be measured in one dimension at a time. So that, including light is three-dimensional to be measured, that gets condensed down into one dimension. And we don't measure things one-dimensionally. So we cannot observe the light escape because it doesn't escape as light. It eventually finds its way around through some form of equilibrium where, in an exchange of information, the black hole gives off Hawking radiation. And eventually, once it runs out of planets and galaxies to eat, it will slowly dissipate across the universe. If you look at what spaghettification is, it's the result of a three-dimensional body compressing information. Now, we look and it's just something gets thinner and thinner and thinner until it becomes one-dimensional. That's the end. And when it's there, it's below the event horizon. And we call it the event horizon, but really it's the three-dimensional event horizon because there's still a single or two-dimensional information in there, packed tight, but not forming or organizing into three-dimensional space. Now there's the wave nature of particles that we have to talk about. When they're moving, there will emerge multiple paths through this time geometry that hold the same difference in equilibrium relative to everything else in the universe that has enough pull on them to matter. And just as Feynman proposed a sum of histories, this would hold true for a particle until the states change that made one path the most in time sync with its surroundings. In this way, we have a specific reality form once the scale becomes appropriate. In this way, the observer effect will change measurements on atomic and subatomic scales because the informational clusters that make up particles seem to travel as waves. Now, entanglement, this is another one that at first I was not quite sure how it worked, but it does fit in with all of this. There's a possible connection in lower dimensions that does not experience traditional time the same. In other words, if you twist and warp this time geometry in a certain way, as this changes at the speed of light, you can instantaneously move some information across it in the first dimension. This sort of axis of rotation, like the center of a Rubik's Cube. As you twist to a certain state, some connected portions will remain connected even across incredible distance. This is what quantum entanglement is. One particle, one cluster, has a path connecting it to another particle, and as the universe warps, this string of information between them stays complete, stays intact. Now, when you observe or adjust the universe, you can shatter it. It's sort of like string theory, but it's not what makes up all of the universe. It is a byproduct of the structured geometry of the universe. Now, because we can't measure currently to the Planck pyramid geometry level, you could describe the universe as these strings and get a good expression of it. And that's why string theory has been chased so far, because it does almost quite the job. And I saw a theory somewhere, Hopf vibration, which was being used to model certain things in physics. These might be functional models that describe the universe well enough. Now, what is the purpose of all this confusing, complicated, and not quite perfectly put together stuff that I'm saying? Well, I need help. If there's errors in my interpretation or logic, I'd like people to point them out. If there's alternative geometries that express this better, please show me and we can go off those. I don't have the math skills, so if people who do want to make proof or disproof of any of this, please, because if I'm wrong, that's just as good as being right, because that means I've learned things. And then last of all, just even if you don't fully understand or you just think it's cool or you are a serious physicist and you want to explore this, please spread the idea of a universe where all the dimensions are time. Because that's really what's most important, what I want to explore. All the rest of this, like the last 50 minutes of this, could just be thrown out the window. For all I care, as long as we start exploring the idea of 4 dimensions of time to describe the universe. I've seen people doing math models to show it as a 2 plus 2 or a 1 plus 3 instead. And that's very intriguing, very interesting. Lets you do a lot of stuff. I think when Minkowski and Einstein separated space and time, I think they made a mistake. And I know that's a very controversial thing to say, that Einstein made a mistake on this particularly, but I think we just need to look at it a little different, and I think it'll reveal a lot more to the universe and very much describe what is happening. I read all these articles about these new quantum breakthroughs and particle descriptions. We've recently done more modern models of the shape of an electron. Just fascinating stuff. And I think this can continue to help. I don't think it'll invent time travel or perpetual motion or anything like that. But please, give me help. Thank you for listening or watching or whatever you're doing to this. Really appreciate it. And I'm really hoping that something comes out of this, because I would like to go into the physics field and get a degree eventually and work on this, solve this. I mean, this just started with me asking, come on, someone's got to be able to figure this all out and really trying to figure out what we're trying to figure out. So thank you so much.